Winter 19, paper 42, we are going to look at a question regarding ultrasound, specifically focusing on ultrasound's attenuation and reflection on certain boundaries. But first, let us define what is meant by specific acoustic impedance, or your Z value. Okay, so you should remember that the Z value is calculated using the product of density times the speed of sound, rho C. So we'll just write that down. This would be the product of density of a medium, of this medium, and the speed of sound traveling in the medium. Okay, so 1 mark is for product of density and speed, and the other mark is for you mentioning that it is the speed of sound in the medium. Of a medium. Talk about the medium. Okay, medium here is fat, muscle, bone, etc., etc. Okay, part 2. The density of a sample of bone is 1.8 gram per cm cube, and the speed of ultrasound in the bone is given. Let me zoom in a bit for you. Okay, so you are given the speed of ultrasound in the bone. Calculate the specific acoustic impedance of the bone sample. Well, before I start, we're going to check the unit here. Everybody down here, okay, my head is blocking the unit, but every unit down here is SI. SI means all this you need to change, or this one you change to SI. Okay, so first things first, I'll convert the density. If 1.8 gram per cm cube, so in the interest of time, I'm just going to take the shortcut, which is to multiply this by 1000. Okay, so this will be kg meter -3. If you're unsatisfied, think about your AS and unit conversion and try to work it out for yourself. Okay, because it's just 1 mark. So Z is equal to rho C. I will multiply 1.8 times 1000, and the speed of the ultrasound in bone is 4.1 times 10 to the power of 3. Okay, so pressing this in my calculator, I'll just take 1.8 times 4.1, and that will give me 7.38 or 7.4, I guess, times 10 to the power of 123 times 3, 6. 7.38 times 10 to the power of 6. You can write 2 as F. That is perfectly fine. Okay, part B. A parallel beam of ultrasound passes normally through a layer of fat. Okay, so we have a layer of fat here, which I'm going to color yellow, because we all know fat tend to be yellow color. Okay, and then another layer of muscle. All right, so we have fat and muscle in our structure. And the fat has a thickness of 0.45 cm. Okay, and the muscle has a thickness of 2.1 cm. All right, so muscle got a lot of blood. So I'm just going to shade this a general shade of red. Okay, just to help us distinguish. So I want you to identify a few things that's probably going to happen here. Number one, there's a certain boundary. You may be asking me, Miss, where is the boundary? Boundary is always between two medium. So there are a few mediums here. The first one would be the air and fat, which hopefully they will use a gel, so that is about the same. But the main boundary I'm guessing here is between fat and muscle. So I'm just going to draw a dotted line here to remind myself that I probably need to go and look at this boundary later. Okay, great. So let us continue. Data for fat and muscle is given. So you are given the Z value, which is the specific acoustic impedance. You're also given the linear attenuation or absorption coefficient, your mu. Note that the mu is given in cm -1. So the thickness, you have to stick to cm. We're gonna stick to this unit. Okay. All right. So I think we're good to go. Let's see what the question wants from us. The intensity reflection coefficient alpha at the boundary between two media of specific acoustic impedance Z1 and Z2 is given by this expression. Very nice. The value of alpha for your boundary is given If they give you, you need to remember lor, okay? So you're given the equation to find alpha. They don't always give this to you. Sometimes they do. So make sure you know how to find the intensity reflection coefficient. Okay? Calculate the fraction of intensity of ultrasound that is transmitted through the boundary between fat and muscle. Okay, so it's worthwhile to remember that this alpha value here, it carries the meaning of a reflected intensity. So I reflected over the incident intensity. Either you put I naught or I incident. All right, so let us find what is the value of alpha first. Okay, and for convenience, I have placed the table here. Right, so we're going to use the value of alpha, which is 1.3 and 1.7. I mean, sorry, the value of Z. So this is my Z values. Okay, I'm going to use this. I'll write here for us. I mean, of course, you're going to write here during the exam. So yeah, I'm going to use the equation now. It doesn't really matter whether you take the bigger number minus the smaller number because you're going to square it anyway. All right. And another pro tip here is to not even need to include the prefix. But if you're feeling insecure, by all means, go ahead. This whole thing power 2 divided by 1.7 plus 1.3 times 10 to the power of 6. This whole thing power 2. Okay, please don't cancel off the square. If can cancel, they early also cancel already. Yeah, so you don't cancel the square. All right, so actually what you need to do, because the 10 to the power of 6 will disappear, because you can bring them together under the same square, under the same index. And then this will be 1.7 minus 1.3 over 1.7 plus 1.3. I'm going to ask my friend Casio, the calculator, what is 0.4 divided by 3? Ding, 0.1333333 square. Ding. 0.17777. So we'll put 0.01777, then 0.018. Okay, or 0.178. USF is good enough. So this is the reflected, because this is IR over I. IR over I. Okay, so if you think about your boundary, okay, I'm going to draw the boundary here. Here is fat. Here is muscle. Okay, your fat and muscle. And right now, the one that is incident is I. Okay, let's say this is I not lah. But it's at the boundary though, so I think I should just draw it a bit carefully. Now here, hitting the boundary is I. Okay, transmitted is, let's say, IT. Reflected is IR. So in this case, right, if they want the fraction of intensity that is transmitted, okay, what do? We know that I is equal to IT plus IR. So I guess we can use this relationship. Let me adjust the screen a bit so you can see. So I'm going to use IT plus IR. Okay, so in this case, right, since this I is assumed to be 1, I guess if you want to, okay, let me rearrange. This is for us whose brain, and if you and ratio are not best friend, it's a bit sad. Your life is going to be a bit longer, but no harm done here. So this is IT, and what is your IR? 0.018. Can? So you bring this around, then you will find IT is equal to bracket 1 minus 0.018. Okay. What is happening here is this IR, I highlight for you lah. This IR is this much in terms of I. There? Here ma? Okay. So then I bring this 0.018I over to minus. So I minus 0.018I. So 1 minus 1. Okay. So again, if you are fast, you can immediately tell that now IT over I, you bring the I over to divide ma, because this is the fraction that they want. This fraction, fraction of transmitted ultrasound is the ratio of IT over I. This is what they want, IT. Okay, so we have IT over I now because we can just bring over and minus. So it will be 1 minus 0.018. So this means most of the ultrasound will be transmitted, and that would be 0.998. Hang on, brain hang. 1 minus 0.018. 0.982. Ah, yes. Over I. So the fraction, final answer, IT over I is equal to 0.982. So what they actually expect you to do is to find, because this is only 1 mark, So they expect you to substitute 1.7 minus 1.3 over 1.7 plus 1.3 square. That will be your first mark. I mean, that will be the first step that they want to see, leading to 0.018. And then you do this 1 minus. So your actual working is just here. You get a 0.018 and then you 1 minus the answer. So if you cannot brain why is it 1 minus, then you just take a bit of time to draw out the picture. We incident 1, transmitted 98.2% because we reflected only 1.8%. This is what the numbers mean. I read for you. Incident 100%, transmitted 98.2%, reflected 1.8%. Okay, so this is what these numbers mean, and this is what the value of alpha brings to us. An understanding of the fact that sometimes when ultrasound hit a boundary, some will go in, some will reflect, depending on why we are ultrasound and what we want to see. Sometimes it's favorable, sometimes it's not. Okay, now it's time to move on to the second part. So when is it favorable and when is it not? Go and look up the lecture value and see what does the Z value represent. What happens when this number is very small? What happens when this number is close to 1? That is a pretty important past year question. But in this question, we're not going to talk about that. We are going to move on to the next phase, which is attenuation. Okay, so attenuation, if you remember, is the decrease, the decrease in intensity as a wave travels through a medium. Okay, so a decrease or a reduction, I guess you could use the word decrease in intensity of a wave. So in this case, it will be the ultrasound wave as it travels or passes through the medium. Okay, so hopefully you've watched the video and you understand that when things travel, they will lose energy. Okay, next. The data for linear attenuation coefficient is given in figure 5.2. So let me magic out the figure 5.2 for you. Ta-da! Sorcery and magic. Okay, call cut and paste. So determine the ratio of intensity of ultrasound transmitted through the medium. So we want transmitted to incident. For the layer of fat of thickness 0.45 cm, okay, and the layer of muscle thickness 2.1 cm. Thank you for telling us this. You don't have to scroll back and look at the picture. Yeah. Okay, and using your answers in B and C to determine the fraction of intensity entering the layer of fat that is transmitted through the layer of muscle. Okay, one by one, we do these two first. This one is easy claps. Okay, so we want to know how much ultrasound is passing through the media. So let me draw out the boundaries again for us. Okay, there we go. Fat and muscle. All right, and we have ultrasound going into. Ultrasound is going into the muscle. Let me adjust this sound. Ding, ding, ding. Okay, ultrasound is going into the fat. Sorry about that. So we have to be a little bit intentional in labeling our eyes. Okay, so I think intensity of ultrasound entering the medium or fat, let's call this at this point here I naught lah. This is the virgin ultrasound, haven't passed through any medium yet. Okay, then this ultrasound will attenuate, become weaker and weaker, such that let's say when it reaches the boundary, I will call this ultrasound I1. Okay, so the ultrasound that reaches the boundary is I1. So now I'm looking for I1 over I0. Okay, after passing through 0.45 cm of fat. All right, recall the equation for linear attenuation for ultrasound. I, which is the same as X-ray, by the way, I naught E negative mu X. Does that sound help you remember the equation better? I don't know. All right, so the incident one is I naught, so I'm just going to keep this as I naught. Okay, so right now we will have I1. So this will be I naught E negative mu X. All right, the I naught and I naught will go away. So we have negative. The mu for fat, what is it? What is it? Fat is 0.24 here. So we're going to take 0.24 multiply by 0.45. The thickness. Okay, so as I mentioned just now, we want to stick to cm. Okay, so press my friend the calculator. 0.24 times 0.45. Don't forget the negative. Okay, that would give us a number of 0.8976. 0.90. 8976. I write a bit more number first lah, then I round it up lah, if it makes you uncomfortable. You can't put 0.897. 898. 0.9 is fine. 2SF is good. All right, moving on. Layer of fat. Okay, so we're going to do the same thing again, but it says entering the medium. Sure, you can put this one I1 and then pass through everybody. So here is I1. Just gonna maybe put red. So when we enter here, incident entering the medium. This entering is actually the transmitted ultrasound, whatever that ratio is lah. Okay, so I think just to make sure we are not the confusion, I'm going to redraw the muscle boundary again. Okay, so by the way, all these drawings will only help you if you need it lah. Okay, if you can brain it, it's not a problem. So right now, the one that is going in is IT, not I1. I1 that reaches here from the fat layer, part of it will go in, but part of it will reflect. Remember, this is IR. We talked about this just now in the previous Z value. So we are looking at IT, okay? And then at the end of my 2.1 cm of muscle, what is this I? So at the end of here, let's say here is the end of your muscle. What is this I? Okay. So this situation here necessitates the same equation. You're going to use the same thing, but I will just differentiate out the value of I a bit clearly because later they want us to bring it all together. Okay. So the layer of muscle to the layer of transmitted inside the muscle. So entering is IT, transmitted into the muscle. Just like this I naught is the one that is entering the fat. We assume 100% going to the fat lah, okay? Fat layer, IT, and then up here will be, let's say, I. Okay, so down here will be IT. But the one that goes in here, because this is your maximum value, this one here, right? So the equation that you will use now, your I naught is substituted with IT because of this. So this will be IT E negative mu x. Once again, the T and T will disappear. So we will basically repeat the same calculation. And the only difference here is now we will use a different mu value. Your mu is 0.23 negative 0.23 over 2.1 cm of muscle. Okay, so this one is relatively straightforward. You don't have to complicate it until the third point. So I'm just laying down the foundation for the third part D lah. This is 2.1. So this will give us 0.6169, 0.62, sticking to 2SF. All right, so 3 marks. So whenever it is as simple as enter and transmit, you can just use the equation E negative mu x, because the entering one divide by, the transmitted one divided by the entering one, they will have the same initial values. I naught, so they cancel out. Okay, IT, so they cancel out. But now we're going to put them together. Using all this fraction, determine the fraction of intensity entering the layer of fat that is transmitted through the layer of muscle. Okay, pretty interesting stuff. So we're going to take the fraction of, and this is 1 mark only, intensity entering the layer of fat. Again, what did I call this? Entering the layer of fat will be I naught. That is transmitted through the layer of muscle. So this is I naught. Okay, and then through the layer of muscle, go back to my diagram, through the layer of muscle is I. This one, so I. Okay, let us try to think about what fractions to use. Okay, so this is the same drawing again. I pasted it here. So entering the muscle layer is I naught. Okay, and we know that reaching this layer after transmission, this I1, I'm going to write here, I1 is 0.9 I naught. 90% of the ultrasound will be left at the boundary. Okay, how much is being transmitted? Let's say transmitted is IT. So IT will be how many percent of the incident? We have calculated this one. What is the transmitted fraction? Let's go back to part B when we looked at the Z value. Okay, here. The transmitted one is 0.982 or 98. I guess to be consistent, if I take 3SF, everything should be 3SF lah. I'm going to stick to 0.98, okay? So that would be 0.98. Okay, so 0.98 of I1 will go into the muscle. Some of it will reflect 982 lah, but we'll stick to 98. Okay. All right. So they want this. They want it through the layer of muscle. So we need to reach to the very end. Very end here is I. Okay. And I, previously we have calculated, transmitted through the muscle is 0.62 of IT. I1, IT, I1, IT. Okay, so let's think about this. Ultrasound about to go into fat. At the end of the fat layer, 90% is left. 90% of the ultrasound is going to pass through the boundary. After passing boundary, 98% of the 90% is left. At the end of the muscle, 62% of the 98% of the 90% is left. Okay, or you could just look at these numbers and multiply them lah. You will get the ratio. So you can just then say, hence the ratio of I over I naught will be equal to 0.62. Okay lah, I will show the working, but then you can jump one. Okay, so how are we going to cancel all of this there? You take this IT, put inside here. It's like a Russian doll. Okay, so I have I is equal to 0.62 IT. And what is IT? 0.98 I1. And what is I1? 0.98 multiplied by 0.90 I0. So conclusion, I over I0 will be 0.62 times 0.98 times 0.90, because all these are just percentages or fraction. So you can just bring them all together, 0.62, 0.98, 0.9, and get wrong pressed, 0.5468. So I guess 0.55 or 547. Okay, if the last number is a bit out, it's okay, not a problem. Just make sure that you show your calculation or your working. Okay, so I'm going to write this one 0.55 because we stick to 2SF. So what did we learn here? We learned that every single step, the ultrasound will lose its power, it will lose its intensity. First step, enter the FET, attenuate to 90%. Second step, pass through the boundary, lose another 2%. Or retain 98% of the previous 90%. That's why it's 90 times 98%, 0.9 times 0.98. After you pass through all the muscle, only 62% of the 98% of the 90%. Because every single step you lose ultrasound. So that's why we multiply them. Okay, so this part can be a bit tricky because you may be thinking, do I just multiply all of this? No, sometimes they reflect and come back one. That will be the different example that hopefully you have watched. Is a slightly earlier question, because instead of asking you what is being transmitted, this thing may reflect, right? I will ask you what is being reflected. That can also be asked. All right, so in this example, we learn how to calculate the fraction of ultrasound that reflects using the Z value. We learn how to use the specific acoustic impedance, the Z value, to find your alpha. Please make sure you know what is alpha. We also learn to read the question and also look at the attenuation and ratio. All right, so that's all for this example. Please try some past year questions to level up your understanding and ace A2 together. Share this video with a friend. I will see you in the next one. Bye-bye.